The paper, Walk the Dog, Cross-Morphology Motion Alignment via Phase Manifolds, presents a groundbreaking approach to understanding the periodicity structure and semantics of motion datasets, independent of character morphology and skeletal structure. This novel method utilizes a vector quantized periodic autoencoder to learn a shared phase manifold for multiple characters, such as humans and dogs, without supervision. The phase manifold consists of multiple closed curves, each corresponding to a latent amplitude. Semantically similar motions from different characters are embedded into the same curve of the manifold, and motions within the same component are aligned temporally by the phase variable. This is achieved by leveraging the discrete structure and a shallow network as bottlenecks. The authors demonstrate the manifold's capability in timing and semantics alignment in several applications, including motion retrieval, transfer, and stylization. The learned phase manifold, visualized in Figure 1, shows that semantically similar motions from different characters are clustered into the same curve, enabling cross-morphology motion alignment. The paper's contributions are rooted in the machine learning and motion processing domains, with a focus on character animation and motion alignment. The proposed approach has potential applications in various fields, including computer graphics and interactive techniques. The authors introduce a groundbreaking approach to character animation research, focusing on the intrinsic structure and semantics of motion. Unlike existing methods such as motion graphs and motion fields, which rely on extrinsic pose features, this novel approach aims to learn an intrinsic motion representation that is independent of character morphology. This representation can disentangle motion structure from semantics without any labels or supervision signals. The proposed latent representation decomposes motions into a 1D phase variable and discrete amplitude vectors, forming a disconnected 1D manifold. This manifold consists of multiple connected components, each corresponding to a discrete amplitude vector learned through vector quantization. The discrete amplitude vectors serve as a narrow bottleneck to regularize unsupervised learning of semantic motion clusters. The authors formalize this approach as a vector quantized periodic autoencoder, VQPAE, which embeds motions into a disconnected 1D manifold. The VQPAE consists of an encoder that projects a short input sequence into a 1D continuous phase variable and a latent code from a small codebook, and a decoder that reconstructs the input sequence using a simple two-layer convolution network with limited capacity. The codebook and autoencoder are jointly learned end-to-end. The effectiveness of this approach is demonstrated by learning VQPAEs from both human and dog datasets with a shared codebook, resulting in a highly structured and aligned phase manifold. This manifold enables flexible integration with existing motion synthesis pipelines, allowing for motion retrieval, transfer, and stylization. The authors highlight their key contributions, including a novel phase manifold designed for both timing and semantics alignment, and the use of narrow bottlenecks and intrinsic structure of motions to achieve alignment among heterogeneous datasets without any supervision, self-supervised losses, or skeletal structure correspondences. They also review related work on clustering and organizing motion capture datasets, motion retargeting, and style transfer. The Walk the Dog technique is a groundbreaking approach to cross-morphology motion alignment, leveraging phase manifolds. Building on the success of Deep Phase, which introduced periodic autoencoders (PICE) for learning on a continuous and expressive multidimensional phase manifold, Walk the Dog innovates by disentangling phase manifolds. This disentanglement enables the separation of timing and high-level semantics of motion, significantly advancing motion alignment and synthesis. The Walk the Dog architecture comprises a vector quantization phase amplitude encoder, VQPAE, which processes short motion sequences to predict phase, frequency, and amplitude. A convolutional decoder then reconstructs the input motion from these predictions. Vector quantization ensures the structure of the phase manifold, and a shared codebook among multiple VQPAEs facilitates alignment across different characters. Inspiration is drawn from various previous works, including Park et al.'s keyframe alignment, Anuma et al.'s styled transfer in the frequency domain, and the introduction of phase into neural networks by Holden et al. The authors compare their method with Deep Phase, highlighting the advantages of disentangling phase manifolds. Furthermore, the paper discusses motion retargeting and style transfer, areas where WalkTheDog can achieve similar effects by treating each style as a separate dataset and leveraging its alignment ability to transfer content. In summary, WalkTheDog presents a significant advancement in motion alignment and synthesis, particularly in handling complex, non-periodic motions and enabling a shared phase manifold for multiple characters. The authors propose a novel method for learning motion manifolds in computer graphics, introducing the vector quantized periodic autoencoder, VQPAE. This approach aims to learn motion embeddings from a dataset and map each frame of an input motion sequence to a point on a phase manifold. The phase manifold is constructed using a 1D phase variable and a vector amplitude, with the mapping function psi being an ellipse embedded in R(d). The VQPAE architecture consists of an encoder that predicts the amplitude, phase, and frequency at the center frame of a short input motion sequence. A phase calculation module is used to predict the phase and frequency, while a vector quantization layer is employed to cluster the amplitude vectors into a learnable codebook. A decoder then reconstructs the input motion sequence from the predicted embedding. The authors use a loss function that includes a reconstruction loss for the VQPAE and a vector quantization loss. They demonstrate the effectiveness of their approach by visualizing the phase manifold and showcasing the flexibility of their method in learning motion manifolds from different datasets. This work contributes to the field of computer graphics and machine learning, providing a new tool for motion analysis and synthesis. The authors propose a novel approach, WalkTheDog, for cross-morphology motion alignment via phase manifolds. This method involves training multiple vector quantized product of autoencoders, VQPAEs, on diverse datasets, ensuring a common phase manifold by utilizing a shared codebook A. The total loss function is a combination of reconstruction loss and vector quantization loss, with a hyperparameter lambda VQ to balance the two terms. To align motions among different datasets, the authors learn a common phase manifold among VQPAEs without additional supervision. They illustrate the training process for two VQPAEs on two datasets with different skeletal structures, which can be extended to more datasets. The loss function for training two VQPAEs is a combination of reconstruction losses and vector quantization loss. The authors adapt a reinitialization technique proposed by Jung and Vidaldi, 2023, for training with one VQVAE to address the issue of disparity in embeddings. This involves updating the decade running average usage of each entry in the codebook A by the VQPAE and reinitializing the less frequently used entries to a randomly chosen amplitude produced by the encoder. Unlike existing methods that require partially specified skeletal topology correspondences and additional implicit supervision, the author's method achieves a common phase manifold with only a shared codebook A and no additional supervision. The phase manifold can be used to model different character topologies, including biped and quadruped, without extra class-specific designs. After training the VQPAEs, the authors obtain the corresponding manifold embedding for every frame in the dataset. They demonstrate that motion matching on the phase manifold can be used to retrieve a motion sequence from the database, with the phase embedding as the control signal. The explicit phase variable improves the motion matching algorithm, allowing for more expressive and flexible motion retrieval. The authors present a novel approach to motion transfer and stylization using a 1D phase manifold, outperforming skeleton-aware networks, SAN, in handling motions with diverse frequencies and skeletal structures. To address motions with different frequencies, they introduce frequency scaling, as shown in Figure 5. This innovation overcomes the limitations of vanilla motion matching, which can result in timing or semantics misalignment. Algorithm 1 performs frequency-scaled motion matching on a fixed number of cycles, rather than a fixed number of frames, enabling more responsive and smooth motion transfer. This algorithm employs a phase manifold to define the period of a motion sequence and queries every period of the input manifold to achieve accurate timing and semantics alignment. The transition cost function C(I)(k) is defined in equation 9, which considers the similarity between frames, pose descriptors, and frequency differences. Additionally, the authors introduce a third term to favor motions with similar frequencies and discourage large temporal interpolation. The proposed method is evaluated through applications in motion matching, motion transfer, and motion stylization, using 3 datasets: dog, human locomotion, and mocha. The authors train their VQPAEs with different dataset combinations and demonstrate the effectiveness of their method in achieving motion alignment and stylization. Furthermore, a small MLP is trained for each dataset to minimize the loss function in equation 10, obtaining the average pose at each point of the manifold. This verifies the alignment effect of the 1D phase manifold. WalkTheDog is a novel motion alignment method that leverages phase manifolds to synchronize motions across different characters and datasets. This approach is particularly useful in scenarios where semantic or timing alignment is not well defined, such as aligning motions of a dog and a human. By retrieving motions at different frequencies within the same connected component, the authors demonstrate the effectiveness of their method. Additionally, they showcase the ability to disentangle phase and amplitude, allowing for the creation of a more robust phase manifold. The proposed method has potential applications in motion stylization and characterization, enabling the transfer of core motion content among different characters. To examine the impact of codebook size and reinitialization on the performance of WalkTheDog, an ablation study is conducted. The results indicate that a codebook size of 32 for the human dog setting and 64 for the stylized setting strikes an optimal balance between expressiveness and manifold overlapping percentage. WalkTheDog offers a promising solution for cross-morphology motion alignment, with potential applications in various fields including computer graphics, robotics, and virtual reality. By leveraging phase manifolds, this method can effectively synchronize motions across different characters and datasets, even in scenarios where semantic or timing alignment is not well defined. The ability to disentangle phase and amplitude enables the creation of a more robust phase manifold, further enhancing the method's effectiveness. This research paper introduces a novel motion alignment approach using a disconnected 1D phase manifold. It leverages the intrinsic periodicity of motions and utilizes vector quantized periodic autoencoders, VQPAEs, to embed motions from different characters into the same phase manifold without supervision or skeletal structure correspondences. This technique can be integrated with motion matching for applications such as motion retrieval, transfer, and stylization. The success of this simple motion alignment is attributed to the limited capability of the shallow VQPAE, which prevents large distortions between the motion representation and the latent embeddings, and the design of the compact latent space. For semantic alignment, the structural similarity between motion datasets is explicitly reflected in the latent space through the amplitudes. For example, running motions are clustered into ellipses with larger amplitudes, while idling motions are clustered into ellipses with smaller amplitudes. The anisotropic structure of the ellipses is crucial for timing alignment, ensuring that crucial points in motion such as foot contacts are mapped to the vertices of ellipses. Although the alignment is not always perfect, the framework provides good timing alignment. The semantics alignment is not always perfect either, requiring carefully picking the right codebook size to balance between expressiveness and the amount of overlap among datasets. Future directions include automatically learning the size of A and filtering out motions that are not semantically similar. Additionally, the residual amplitude, removed by the quantization, could be potentially used for representing styles of motions within the same semantics. The current framework is not generative, and exploring the possibility of generating new motions from the phase manifold could be a promising direction for future research. In the realm of motion alignment, phase manifolds have proven instrumental in capturing periodic motion patterns. Early work by Unuma et al. 1995 laid the foundation with Fourier principles for emotion-based human figure animation. Subsequent research built upon this, exploring motion blending, Park et al. 2002, physics-based character skills, Peng et al. 2018, and robust 3D pose estimation, Shi et al. 2023. Deep reinforcement learning has been employed for character skills, Peng et al. 2018, while latent diffusion models have enabled high-resolution image synthesis, Rombach et al. 2022. The importance of phase-conditioned human motion priors, Shi et al. 2023, and 3D dance generation using actor-critic GPT with choreographic memory, Li et al. 2022, has also been highlighted. Recent advances have seen motion in between and with phase manifolds, Starke et al. 2023, periodic autoencoders for learning motion phase manifolds, Starke et al. 2022, and neural state machines for character-scene interactions, Starke et al. 2019. Additionally, local motion phases have been used for learning multi-contact character movements, Starke et al. 2020. And physically based motion retargeting filters have been developed, Tak et al. 2005. Furthermore, neural discrete representation learning, Van den Oort et al. 2017, neural kinematic networks for unsupervised motion retargeting, Villegas et al. 2018, and real-time styled transfer for in-labeled heterogeneous human motion, Shaw et al. 2015, have been explored. Modi-adaptive neural networks have been applied to quadruped motion control, Zhang et al. 2018, and generating human motion from textual descriptions with discrete representations has been achieved, Zhang et al. 2023. This paper introduces a groundbreaking framework for motion transfer between characters, ensuring the preservation of motion semantics. As shown in Figure 7, this approach successfully transfers motion between different characters while maintaining semantic coherence, outperforming the state-of-the-art method, SAN 2020A, which produces unstable results due to adversarial training. The proposed framework facilitates phase and amplitude disentanglement, as illustrated in Figure 8, allowing for the generation of motion that combines the semantics from the amplitude input and the timing from the phase input. In contrast, Deep Phase 2022 fails to achieve this disentanglement, resulting in implausible motions due to an entangled phase manifold. Figure 9 demonstrates the motion characterization capabilities of the proposed framework, successfully transferring the walking motion of an ogre to a clown while preserving the motion semantics. The resulting motion is highly characterized, highlighting the effectiveness of the approach. The key to this framework's success lies in its ability to decouple the phase and amplitude components of motion, enabling the transfer of motion semantics between characters. This decoupling is achieved through a novel optimization process that ensures the preservation of motion characteristics. The proposed method offers a significant improvement over existing approaches, which struggle to maintain semantic coherence during motion transfer. By addressing the limitations of current methods, this framework has the potential to revolutionize the field of character animation, enabling the creation of more realistic and engaging animations. The WalkTheDog system's phase calculation module and motion matching algorithm are detailed in this supplementary material. The phase calculation process, based on Mason's equations, 2022, utilizes a one-channel signal and relative timing to calculate the phase. The motion matching algorithm, outlined in Algorithm 1, uses phase embedding sequences to retrieve motion sequences from a database. It employs a simple setup with normalized joint positions as the pose descriptor and applies inertialization at each transition. The cost function in Algorithm 1 can be customized based on the specific application. This supplementary material also includes a detailed description of the datasets used in the experiments, including their frame rates and the number of frames. Training times for these datasets vary, ranging from 40 minutes for dog and human locomotion to 2 hours and 40 minutes when training on all datasets together. In their research on motion synthesis, the authors detail the network architecture and hyperparameters used for training. The convolutional encoder and decoder share a twolayer 1D convolution with a kernel size of 23, utilizing ELU as activation. The multi-layer perceptron (MLP) producing raw amplitude consists of 5 layers, with hidden units of the same size as the amplitude. Similarly, the MLP in the phase calculation module also has 5 layers, with hidden units the size of the input frequency bin powers produced by fast Fourier transform, FFT. The MLP used in learning average poses comprises 8 layers, with hidden units the size of the pose, and uses leaky ReLU with a negative slope of 0.2 as activation for all MLPs. The authors implemented their variational quantized phase amplitude estimator, VQPAE, in PyTorch, performing experiments on an NVIDIA GeForce RTX 3090 GPU. They optimized the network parameters using the Atom Optimizer with a learning rate of 1 × 10⁻⁴ and a batch size of 32. They chose to use joint velocity in the local coordinate of the character as the input feature x, with the size of the input motion sequence during training corresponding to 1 second, varying slightly for different datasets based on their frame rate. For the hyperparameters used in frequency-scaled motion matching, the authors set lambda equals 0.5 and lambda equals 1. They also provide a list of hyperparameters used in their experiments.